Okay, today's lesson we're going to move on with our derivatives. If you remember from before, our first derivative equation gives us slope. So if I had something like our first derivative equal 2x minus 4, so we could take that equation and figure out where the slope is equal to 0. So when we solve that, we would get, in this case, x equals 2. So remember, with first derivatives, that's telling us that we have something going on at 2, but we need to test either side to figure out whether the slope is positive or negative or whatever. So if we try something like a 1 into this original equation, we would get a negative answer. If we put something like 3 in, we would get a positive answer. So that would tell us that our slope is negative, changing to positive. Therefore, at 2, we would have a minimum. Okay, so that's what we kind of did previous, but what the issue is with second derivatives or with first derivatives is sometimes we don't know if it's a max or min, and sometimes it's neither. It could be like if we did an equation like y equals x cubed, the first derivative would give us x squared, 3x squared, so if we make that equal to 0, we would still get 0 as a solution. But if we do our test points for this one, we would have positive on both sides. So what that means is 0 is not a max or a min, it's just a place where the slope is equal to 0. So if we look at a cubic graph, we can see that our slope is indeed 0 at the origin, but it's not a max or a minimum. So this is where today's stuff's going to make it a little bit better. A second derivative will give us a bit more information, and it'll help clarify a lot of those things of whether they're maxes or mins or not, or something different, and so on. Okay, so the first thing we'll go through is a few definitions and terms to make sure we're up to speed in the words, and then we'll look at some examples. So I was just saying on the previous page, we know that our first derivative gives us the slopes, which can help us figure out if there's maximums or minimums. The second derivative will also give us some information, but instead of being slopes, it's going to give us concavity. So we're going to be able to determine the concavity of the graph at those certain locations, and that would then help us determine whether it's going to be a max or a min, but it'll also give us the locations of what we call inflection points. So for that graph that I just had on the previous page, when we do y equals x cubed, that origin where the graph turns is what we're going to call an inflection point. So the concavity, what we're talking about with second derivatives, if the first derivative is slope, concavity is telling us how quickly the slope is changing, or the slope of the slope. So what happens is we're looking actually at the curvature of the graph. So if we have something that curves upwards, like it is here, you can see on this side of the graph, it's curving upwards, so we would call that our positive concavity, or it'd be called concave up. And then anything that's curving downwards, which would be like the left side of this graph, that would be our negative concavity, or concave down. So if you look at these graphs, what's interesting with concavity is no matter where we look at it, the graph is always going to be either above or below the tangent slopes. So if I was to do a couple of tangent lines on this graph, this one might have a slope of 1. If I pick some other coordinate on that curve, maybe we have a slope of 2. And if I pick somewhere else, maybe we get something like a slope of 5. So you can see as I go along that graph, the curvature is changing, but it's always going to get bigger and bigger. So a positive concavity or concave up means our slope is going to increase more and more as we move along. And we would also consider the left part of this happy face curve also concave positive, even though we're dealing with negative slopes, right? If we did the same thing here, we'd have a negative slope value. But as we move along the graph, even though that slope is changing and it's still negative, it's still getting larger, because negative 2 is larger than negative 4, and so on. So everywhere on this graph, as we move from left to right, the slope is always going to be increasing. So a happy face or concave upward graph, that'll always be the case. And the same thing works for concave down. If we look at the one on the right side here, all of these ones would have a positive slope, but they're going to get smaller and smaller. So if that one was, say, a slope of 4, over here we might have a slope of 2, and then near the top maybe it's a slope of 1. Okay, and same thing, we can do the other side of the curve. They'll be negative slopes, but they're still going to get smaller and smaller. right? We might have -1 changing to -2, and then maybe it changes to -5 near the bottom. So as we go from left to right, all of those slopes are decreasing. So concave up is increasing slopes, and it'll look like a happy face type of graph. Concave down, the slopes are getting smaller, and it'd be a sad face kind of graph. And we don't need both curves. It could be, like if I gave you a quadratic, the curve might look like that. So in this case, it is just concave down everywhere, right? It'd be negative everywhere. But if I gave you a cubic graph, maybe it does something like this. So we can see the left side is concave down, but then the right side would switch to be concave up. So how we're going to use this to our advantage is we're going to calculate where the concavity changes from plus to minus, or minus to plus, or more importantly, or similar to what we did before, we're going to figure out where the concavity is equal to 0. So we're going to take any equation, determine the second derivative, solve where it's equal to 0, and then we'll do our test points. So let's do a simple example here right off the start. So if I gave you, let's just do an easy one. So let's suppose we get down to our second derivative and we got an equation something like 3x minus 6, and we solve that equation equal to 0, we can see that x would equal 2. So what that's going to do is it'll help us determine on which side of 2 what's going on with the concavity. So just like we did with slopes, plug that into the second derivative equation. If we plug in something like a 1, you can see it'd be a negative answer. Plug in something like a 3, we get a positive answer. So we can see we're going to be concave down, switching to concave up. So what that means is if our curve is going in one direction and changing and going to the other direction, that means that location, in this case the 2, would be our inflection point. So our inflection point is the point where the curvature changes from up to down or down to up. So in this case, we'd say we have an inflection point at x equals 2. Okay, and we can see the inflection points. It could be a stationary point. We could get a graph like y equals x cubed, where the slope is 0 at the inflection point. But we could also get a situation where we have an inflection point that's kind of more diagonal. So maybe in this case, the slope would be something like a 1. So the slope can be anything at an inflection point. It doesn't have to be a flat line. So that's why we have to be careful, and that's why it's probably better to do the second derivative first, because that'll indicate whether it's an inflection point or not, and then we can work backwards to figure out what those slopes are if we need to. So we'll go through a couple examples. The first ones we'll just look at calculating the inflection point locations, and we'll figure out whether it's concave up or concave down. And then our very last example, we'll put everything together that we've learned so far. So for this first one, we can see that it's just a basic quadratic graph. So we already know from Math 20 even that a quadratic graph like this would be downwards, something like that. So we already know it's going to have a maximum, it's going to be concave down, but let's see if the calculus matches that description. So if we do our first derivative, we'd have 5 minus 24x. If we do our second derivative, we just get negative 24. So negative 24, doesn't matter what x value is, it's always going to be negative. So our number line will be negative everywhere because we don't have an inflection point. So what that means is we're concave down throughout the entire graph, and we can see that does actually match what we know about quadratics, right? It is a downward curve everywhere. The only thing that would be different if I did some other equation, and let's suppose our second derivative was equal to negative 2, it would still be similar, but being negative 2 compared to negative 24, it would be a lot wider of a graph, right? If our slope is changing less frequently, the negative 2 would be a wider graph, or maybe negative 24 is a lot steeper, and it's probably even steeper than what I drew. A negative 24 graph might be, really skinny like that. So depending on what the value is, that'll indicate how much of a stretch there is on the graph, but we're not worried about that too much. We're just going to try to figure out where those inflection points are. So in this case, we had no inflection point, and it was concave down from negative infinity to positive infinity. So our next example, it's a cubic graph. So all we know from Math 30 is we know a cubic graph will go from, and it's a negative cubic graph in this case, we know it should go from this quadrant down to the other. So it could be something like that. but maybe it only has one x-intercept. Maybe it looks something like that. Maybe we have a max and min the way I drew it. Maybe it's just going to have one inflection point and not have any max or mins. That's the part we don't know. So in Math 30, we sort of had to kind of guess a little bit and rely on our calculator and things like that. What's nice with this kind of stuff is we can actually, oops, I don't know what I just did there. But we can actually, yeah, I can't get rid of that, but that's okay, I'll just leave it. But we can actually determine what's going on, how many inflection points there are, where they are, is there a maximum, is there a minimum, all of those kind of details can be calculated quite easily. So do the same thing, take your original equation, calculate your first derivative, so just a basic power rule, calculate your second derivative, we can see we get 2 minus 6x. So let's take that equation, make it equal to 0, and solve it. So we'll get x equals 2 6, or 1/3. So what does that tell us? Well, we know we've got something going on at a third. So let's plug in a number on either side into our second derivative. So if we plug a 0 into that equation, we'd get 2, so that's positive. If we plugged in a 1, we'd get -4, so that's negative. So we know we do have an inflection point at 1/3, right? Because our slope, our curvature is changing from positive to negative. So we have positive 1/3 as our inflection point, and we know that the graph is going to be concave up from -infinity to 1/3, and it's going to be concave down from 1/3 to positive infinity. So just based on that information, we don't know the y-coordinate. Maybe let's figure it out quickly. So if we take our 1/3 and let's plug that back into our original equation, that'll give us that should give us the location of the y-coordinate. So I'll just quickly type it in on my calculator here to see what that value would be. So if we put in 16 plus 4/3 plus 1/9 minus 1/8, no, 1/27. So I'm getting approximately 17.4. So we know just from that, we have a pretty good idea of what's going on. So we have our inflection point at 1/3 and 17, so way up there. We know it's concave up on the left side of it, so our graph's going to be curving something like that, and then it's going to change and go concave down after that. So we have a pretty good idea, and that inflection point definitely helps. So we know we got one x-intercept, so if we were trying to figure out that x-intercept, we could go back to our original equation and solve for that. If we're trying to figure out our max and mins, you can see we have a minimum here and a maximum there. We don't know the exact height of those, but again, we could go to our first derivative and determine those max and mins just like we did yesterday. Okay, let's do another one. This is a 4th degree, and again, because it's a 4th degree, we know it could look like a W graph that has 4 x-intercepts. Maybe it has 1 up high and then 2 down lower, so maybe there's only 2. Maybe it's one of those ones that just has an inflection point, something like that. So again, we don't know what the graph looks like, how many x-intercepts, how many max or mins. This is where the second derivatives will definitely help with that. So if we do our first derivative, we get 4x cubed minus 6, minus 6x squared plus 1. Do our second derivative would be 12x squared minus 12x. So and that's what's nice about this too. Our equations tend to get easier and easier as we go. So now if we make that equation equal to 0 and we factor out a 12x, we just get x minus 1. So that tells us our critical points will be at 0 and 1. So if we do our test points between 0 and 1, we should have a good idea what's going on. So let's try plugging in a -1, and again we're going to go to our second derivative equation. If we plug -1 in there, we'd get 12 plus 12, which is positive. If we plug in a half, that would give us 3 minus 6, which would be negative. If we plug in a 2, we would get 48 minus 24, which is positive. So we can see now we have two inflection points. We have one at 0. And again, we could go back to our original equation, plug in a 0, that gives us negative 2. We have another one at 1. Plug that back in our original equation, we'd get 1 minus 2 plus 1 minus 2 gives us negative 2 as well. So we've got our inflection points figured out. We know it's going to be concave down between 0 and 1. That's what our little number line thing is telling us, right? It's negative between 0 and 1, so we've got that figured out. And it's concave up on the outer intervals, so from negative infinity to 0 and from 1 to infinity. So again, without even doing max and mins or x and y intercepts, we have a pretty good idea what this graph's going to look like. So we have two inflection points. One's at 0, negative 2. Another one's at 1, negative 2. We know it's concave down in between the two, so we know it's going to be some sort of curve like that. What we don't know is how high that is, right? And that's where the first derivative would come in handy. If we calculated the max and mins, maybe it's going to be way taller, maybe it's way shorter. We don't know. But we do know it's going to look like that, and then we do know it's going to curve concave up after that. So we have concave up, concave down, concave up. We know our two inflection points. So our next step to get an accurate graph with this would be maybe to find those max and min locations and maybe even find our x and y intercepts. That would definitely help as well. So that's what we'll do with our last question. Let's take another equation and let's try to solve for everything. So here we have a cubic graph. So we know it should look like some sort of regular cubic, but we don't know exactly where the key points are going to be, but the calculus should definitely help us. So let's do our first derivatives. That would give us 1x squared minus 1x minus 6. Let's go to our second derivative equation right away. So that gives us 2x minus 1. So if we solve that one, we're going to get x equal to 1/2. So again, we have one inflection point at a half. Let's test either side. So if we plug a 0 into that, we're going to get a negative value. Plug in a 1, we're going to get a positive value. So we know we're going concave down, changing to concave up, and our inflection point will be at 1/2. And again, we could plug this into our original equation, and that would help us determine the y-coordinate. So let's do that quickly. So let's go 1/3 times 1/2 cubed minus 1/2 times 1/2 squared minus 6 times 1/2, and that gives us approximately negative 3.1. So we've got our location of our inflection point figured out, so that's great. So let's start sketching our graph and see what we know. So at 1/2 and negative 3, so we're down here somewhere is our inflection point. And we know it's going to be concave downwards on the left side, so it's going to look something like that, and then concave upwards on the other side. So what we don't know is sort of how steep those max and mins are going to be. So let's go back now to our first derivative equation, and let's solve that one. So let's make that one equal to 0. So in this case, because it's a quadratic, we can factor it. So in this case, we've got our max and mins are likely going to be located at 3 and negative 2. The nice part is we don't have to do our number line testing like we did before, because we've already done it with the inflection points. So we can actually just put those on our same number line and see where they would line up. So negative 2 is over here somewhere, so that's going to have to be a maximum because it was concave down. 3 is over here somewhere, it's going to have to be a minimum because it's concave up. So we've actually figured out where those are not where they are, but what they are. So let's label that. So we have a minimum at 3. We're going to have a maximum at negative 2. So again, to figure out our coordinates, let's go back to our original y equation. So if we plug that in our calculator, we'll have 1/3 times 3 cubed minus 1/2 times 3 squared minus 18, and that gives us negative 13.5. So according to my graph, you can see if that was our 1, 2, 3 would be about there. So you can see my minimum definitely isn't fairly accurate. It's going to be way down at negative 13. So our minimum is going to be probably off the screen, but I'll just estimate it down here somewhere. So now we know where that minimum is going to be. So let's do the same thing for negative 2. So negative 2 cubed. And then we're going to go oops, I did that wrong. Let me do that calculation again. So 1/3 times negative 8, so that gives us negative 8/3 minus 1/2 times 4, which would be 2, and then we're going to go plus 12. So that gives me about 7 1/3, so we'll just go 7.3 approximately. So again, I don't have that one quite accurate, so negative 2 is going to be way up at plus 7, so somewhere up here. So now we know where that maximum is located, so that helps a little bit more with our graph. So let's sketch that out. So we know it's going to go through this inflection point, but now it's going to go up to the maximum, something like that. So we've got most of our key features. The last thing that we could do if we wanted to be more accurate is let's figure out our x and y intercepts. So if we go back to our original equation, make x 0, we would get 0 for y. So that would be right at the origin, so that looks pretty close to what I got sketched. And then our x-intercepts, we would take our equation, solve it equal to 0. And this one's not a very nice equation to solve, and I don't think it's going to give us nice numbers. So for this, if you had to do this, just use your calculator, graph it that way, and let your calculator give you those decimal locations. So I won't bother doing those, but they would be somewhere in that neighborhood, probably around 4 or 5, and then somewhere in the negative 3 or 4 range, and that would be it. So could we calculate all of our x and y intercepts, max and mins, inflection points? Yes. If you had all of those, your graph definitely would be accurate. Just in this case, you can kind of see right at our inflection point, right? That's cutting that graph from going concave down, and it's switching it to concave up. So it actually makes a little bit of an S-curve there. It's just kind of hard to see, but it would actually be evident if you had an accurate graph of this equation. And that's it. We'll stop there, and we'll move on tomorrow after that.